Okay. So we're going to today talk about section 5.1. This is about fundamental trig identities. So when we talk about an identity in math class, what we're talking about is like an algebraic statement that's kind of always true. So you can have something that's like kind of a silly identity. Like this, right? Like clearly that's always true. Everybody's okay with that idea? It's like a basic algebra statement. But that's kind of what we mean by an identity. It's just like an algebraic statement that's always true. What we're going to do today is we're going to develop a whole series of trigonometric identities and then talk about how we can use those to simplify trigonometric expressions. So we're going to start with what we'll call the reciprocal identities. And these are all things that we've kind of stated at one point or another, but we're now going to like formalize into an identity and kind of write down. So we know that sine and cosecant are reciprocals, right? So I can say that sine theta is equal to 1 over cosecant theta. Or I could say that cosecant theta is 1 over sine theta. We okay with that? We know that cosine and secant are reciprocals. So we can say that cosecant or cosine is 1 over secant, or that secant is 1 over cosine. And I guess I should say secant theta is 1 over cosine theta. Sometimes I'll get going too fast and forget to say the variable name with it, but everybody still okay? And the last pair of reciprocals were tangent and cotangent, right? So we can say the same thing, that tangent theta is 1 over cotangent theta, or that cotangent theta is 1 over tangent theta. So that's our first series of identities. The next set of identities we're going to talk about are the quotient identities. So if you remember back to when we evaluated things on the unit circle, that tangent was y over x on the unit circle, right? And on the unit circle, the y-coordinate represented sine, and the x-coordinate represented cosine. So really, we can say that tangent theta is equal to sine theta over cosine theta. Is everybody okay with that? If tangent is y over x, and sine is y, and x is cosine, then tangent is sine over cosine. And if cotangent and tangent are reciprocals, that means that cotangent theta is equal to cosine theta over sine theta. right? The reciprocal of tangent. Still doing okay there? Okay. So the next set of identities are called the Pythagorean identities. The first one is that sine squared theta plus cosine squared theta is equal to 1. As a little aside here, that when we write sine squared theta, or sine squared theta, or sine squared x, I guess I would have changed to x's at some point here. I guess I probably, let's just keep everything thetas, huh? Then we write something like sine squared theta. What we're really saying is that we're going to take the sine of theta and then we're squaring our result. The reason we write it the other way, with the sine squared, the squared in between the sine and the theta, is one, we don't have to write this extra set of parentheses. Because if we didn't write those set of parentheses, does this mean that we're doing the sine of theta and then squaring? Or does it mean that we're doing the sine of theta squared? Right? That's ambiguous. We're not really sure what that's representing. That's why we're putting the squared in between the sine and the theta. Is everybody okay with that? So it's just like a weird notation that we're going to use that allows us to not have to write as many parentheses and still be clear about what it is that we're meaning. Because it makes little sense to like square sine, right? Sine is an operation. That'd be like saying, oh, plus sine squared. And you'd say like, what are you talking about, Mr. Gould? Like, that's a bunch of baloney. You can't square a plus sign. You know what I mean? So I just wanted to take an aside there and mention kind of what's going on there. Because it is a weird looking notation, right? Okay. So why is this sine squared plus cosine squared equals 1 true? Well, we've already kind of talked about this indirectly. So if you go back and think about the unit circle, if I pick some coordinate on that unit circle, I can make a right triangle out of that with side lengths x and y. Everybody okay with that? And we'll call the radius of that triangle r then. So I know since I have a right triangle that a squared plus b squared is equal to c squared, or in this case, x squared plus y squared is equal to r squared. On the unit circle, x is cosine, y is sine, and the radius is 1. So that's how we end up with that Pythagorean identity. Is everybody okay with that? So there's 2 more Pythagorean identities. So the first one is 1 plus cotangent squared theta equals cosecant squared. And the second one is tangent squared theta plus 1 equals secant squared theta. Now, where do these two come from? If I take my first Pythagorean identity and I divide both sides by sine squared theta, sine squared theta divided by sine squared theta is 1. Everybody good with that? Cosine squared theta over sine squared theta, well, that looks a little bit like one of the identities that we had mentioned, right? If I go back and look at the quotient identities, I see that cotangent theta is cosine theta over sine theta. Everybody okay with that? So if I have cosine squared theta over sine squared theta, that's really like cosine theta over sine theta times cosine theta over sine theta, right? Which is cotangent theta times cotangent theta, or cotangent squared theta. And if I look at 1 over sine squared theta, this also looks like an identity. If I look at the reciprocal identities, I see that cosecant theta is 1 over sine theta. So 1 over sine theta square, or sine squared theta, I can think of as 1 over sine theta times 1 over sine theta, or cosecant theta times cosecant theta, which is cosecant squared theta. So that's where this identity comes from. It just, I took that original Pythagorean and divided both sides by sine squared. Where do you think I'm going to get the second, or that third identity, excuse me, the tan squared plus 1 equals secant squared? How do you think that's going to come up? I take that first identity and divide both sides by cosine squared. And the same, same kind of thing is going to happen. Okay. 2 more sets of identities, and then we'll do some examples, okay? So the next set are these cofunction identities, are called cofunction identities. So I have a question for you guys before we write these down. On the unit circle, have you guys noticed that like sine of 30 degrees is like 1/2, and cosine of 60 degrees is also 1/2? Do you notice there a relationship between 30 degrees and 60 degrees? A geometric relationship? There's a special name for those pair of angles back in geometry. They're called complementary because they add to give us 90 degrees. Well, it turns out that sine and cosine are equal for all complementary pairs of angles. So if I did sine of 10 and cosine of 80, I'm going to get the same value. Or sine of 37 and cosine of 53 will give me the same value. So we're going to formalize that. So we can say sine of, now we're going to write this as in radians. So instead of writing 90, I'm going to write pi over 2. And this relationship works both ways. Somebody's car alarm's going off, huh? Hope they're not getting stolen in the parking lot. Oh my goodness. Thought it stopped. Maybe it was just resting. It's coming up for air. That's funny because it's a machine and clearly it doesn't need air or rest. The same complementary relationship exists between tangents and cotangents, and also between secants and cosecants.
So are we just like expected to memorize this? Because like really...
Yeah, we'll talk about what the expectation on that is in a second. That's a fair question. So if you notice with all these trig functions we've talked about, sine, cosine, tangent, secant, cosecant, cotangent, that a lot of them are just the same name, but the prefix co in front of it, like sine and cosine, secant and cosecant, tangent and cotangent. Right? We've noticed that, I hope. The prefix co is short for the word complementary. So sine and cosine is like cosine is really the complementary angle version of sine, which is basically what we're just stating here in the identity. So it's easy to kind of remember those complementary pairs because they're kind of naturally paired together because they're the same thing with the co-prefix. Is that okay? All right, the last set of identities here are these odd-even identities. So remember when we were graphing sine, cosine, tangent? At that point, we looked at the graphs and identified whether they were odd or even functions. So for example, sine we observed was an odd function. And one of the properties of odd functions is that f of negative x is equal to negative f of x. I guess we're using thetas. So sine of negative theta is equal to negative sine theta. And if sine is an odd function, its reciprocal function, cosecant, should also be an odd function. So we can say the same thing about cosecant. Cosine, we observed, was an even function. So we can say that f of negative x is equal to f of x. And if that's true for cosine, it should also be true for its reciprocal function. So we can say the same thing about secant, that secant of negative theta is equal to secant of theta. And tangent, when we graphed that, we noted that was odd as well. So we can say tangent of negative theta is equal to negative tangent theta. And again, if that's true for tangent, it should be true for its reciprocal. So we can say cotangent of negative theta is equal to negative cotangent theta. Now, I've collected all of these identities for you guys onto this sheet, the basic trig identities sheet here in the content library. So everything is kind of collected together and typed out, so it's nice and neat and in one place. For this test, this would be part of the notes that would come with your test. Okay, so it's not of a high priority to memorize these things. Although I would say all the things that we do in this chapter become much easier if you're like, you basically have these things memorized. Like everything, it's easier to kind of string things together if you're not consistently having to go back and forth, back and forth, back and forth. So while it's not a requirement to have memorized, and you certainly don't need to have it memorized for the test, you should have it like pseudo-memorized. And that'll kind of happen naturally as we do the problems and are you looking at this sheet kind of all the time and using these things all the time. But I would make sure that I'm well accustomed to this. And I'd probably print my own copy that I have to look at while I'm doing my homework. So I'm not having to just flip back and forth, 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 because that gets a little old pretty quick, right? Okay. So let's do a couple of examples then. So the type of problem that we're going to focus on first, the direction is called, or they're called simplify the expression. Okay, so they're the same. I'm going to switch over to this sheet and drop these note sheets in here, since they already have all the problems written down for us. Okay. So when we're talking about these simplify the expression type problems, we have two sets of tools that we can use to do these sorts of problems. We have like our basic algebra skills, so things like factoring or foiling or making common denominators to add or subtract fractions, or like reducing fractions, right? So basic algebra things, that's something we can use. And then we have these trig identities that we've just kind of discussed. So those are two sets of tools that we can use to do this. When we talk about simplifying an expression, what we want to do is want to find a simpler way of writing this thing. So by simpler, that would mean that like instead of having two terms like we do in this, where we have two things being added together, ideally you'd have one thing, one term. And what's simpler than one term would be, instead of a product of two or three or four things, would just be like a single item. And possibly simpler than that could be just a constant, something with no variable in it at all. Now, we'll have to see as we go through and do these, like, how simple can we make this? Because some of them you can get very simple down to like a constant. Some of them it might be simple as in we get down to a single expression, like a single, like trig function. There's just one thing. Some of them it might not be possible to do more than two or three things, but it just kind of varies. So we're not really sure where the ending is, other than like having a vague notion of what's simpler than one thing is simpler than another thing. You know what I mean? Okay. So if I take a look at the first example, typically the first thing I look for is there anything algebraic I can do? So that's what I'm going to look for first. So here we have sine cubed plus sine x times cosine squared x. Is there anything algebraic I can do? Is there any factoring or foiling or common denominators or reducing or anything like that I can do here? Take a moment, look at it, think about it a little bit. I might even call your attention back to problem number 15 that Victoria asked about from the last homework set as a nice example of what's going on here, because there is something algebraic to do. So notice here that we had signs in both terms. So we could factor that greatest common factor out. Is something similar going on in this example? Yes, right? See that we have signs in both terms. Everybody can see that? So I'll start by factoring out, how many signs can I factor out? A sine x, sine squared x, sine cubed x? Just a sine x, right? Everybody's okay with that? Okay. So when I factor that sine x out, what does sine cubed become? Turns into sine squared. And what does sine x times cosine squared x turn into? Cosine squared x. Everybody agree with what we did there? Is there any other algebraic things I could do here now that we've done this? Not really, right? I mean, we could distribute the sign back through, but what does that do? Takes us right back to where we started. Why would we do that? Okay? So now let's go to our identities and see if there's an identity that looks like it would be useful here. So I'll give you a moment, flip back through your identities, look at what you see, look at what we have here, see if there's anything that looks useful. Again, the goal would be to make things simpler. So you'd want something that takes a lot of stuff and turns it into less stuff, or would allow you to cancel something or combine two things together, something like that. There's a great one here that should be really obvious if you look through and see it. So the Pythagorean identity, the first Pythagorean identity, says that sine squared plus cosine squared is equal to 1. So we have sine squared plus cosine squared. We can replace that then with 1. And obviously 1 times sine x is just sine x. And can we do anything more than that? That's as simple as we're going to be able to make that one. So we're done. Is everybody okay there? All right. Very good. Again, if we have any questions as we're doing these things, stop and ask. Often on these, there's not just one way you could go about doing some of these. There's often lots of different ways that are appropriate. Some of them may take a long time to get there. or you might be chasing, having to use a lot of identities to get there, or some you might be a way where there's just like 1 or 2 identities that you need to use to get there. Yes.
Like I get how you simplified it like the second step, but I'm just confused how you got to like how you distributed it like the first step. I don't understand.
Okay. So imagine that sine is A and cosine is B.
Oh, are we using that formula or is it just like
We're not even using, we're just factoring the greatest common factor. So like I just can factor an A out, and I'd have this, right? Which is what I have here. I have A times A squared plus B. Where just like A's are sines and B's are cosines. You see how it's still kind of the same thing? So all I did was some just factoring thing. I didn't use any identities. Is that okay? You're welcome. And I guess it worth mentioning here, does it matter what variable I'm using in here? As long as all the variables in the problem are the same, whether we call them sine x's or sine thetas or sine beta or alpha or gamma or whatever crazy Greek letter I might write down, it doesn't matter as long as all the variables in your problem are the same. Now, if one of there is a sine x and then a cosine y, that's a different horse of a different color, but that wouldn't happen in this course right now. Maybe later in the future. Is everybody okay? Let's look at this next example then. So here we have the quantity secant x minus 1 times the quantity secant x plus 1 all over sine squared x. Again, typically the first thing I want to do is look for any algebraic thing I might be able to do to make life easier. Can't the top just cancel out? No, because it's like, imagine this is like like a minus 1 times a plus 1. Right, so those aren't just going to cancel out. What would you have to do with that? Jane? Yeah, we could FOIL that out as a difference of 2 squares, right? When I multiply that out, what would I get? Just turn into a squared minus 1, right? Is everybody okay with that? So if we had, instead of a's, we'd have secant x's. That would be like secant squared x minus 1. And then we still have that denominator. Of sine squared x. Is everybody okay with what we did there? So I did use the difference of 2 squares multiplication pattern to do that foiling quickly in my head. You could have also FOILed that out by hand. Would not be wrong to do that. Everybody's good with that? Okay. Do you see any more algebraic things to do here? I don't see anything obvious that feels like it's going to be effective. So let's look for an identity then. Do you see any identities that would come in handy here? This one, it's a little bit trickier to see. So as a helpful hint to you, whenever I see a 1 that's being added or subtracted to something squared, my first place I'm going to is the Pythagoreans. Since all of those identities have 1s and things squared in it, that's the place where I would go. And in particular, for this problem, I would want to be... Okay, come on now. Oh my goodness. Are we gonna... And in particular, I'd want to look at the third Pythagorean identity that says secant squared is equal to 1 plus tangent squared, or tangent squared plus 1. I guess the order doesn't really matter. Why is that going to be a nice thing? Because I can add the 1, positive 1, and the negative 1 to get 0. Lily?
Why is the +1 then?
So the secant squared x is equal to tangent squared x plus 1. That was our Pythagorean, one of them. And we just read it, we used this one, but we read it from that direction. Do you see it?
Yeah.
I'll just leave that there for a moment so if people are looking. So that gets us to tangent squared x over sine squared x, right? Which is good. Now we've gotten rid of the addition and subtraction going on. We're down to a single fraction. Can we do better than this? Almost surely we can. The reason I know that is because if you look at the quotient identities, you'll see that there's a way to rewrite tangent in terms of sine and cosine. So it's very possible that I can cancel the sines in the denominator with the sines in the tangent. So what I'm going to do here is I'm going to think about this instead of as a fraction. So I'm going to think about it as the numerator times 1 over the denominator. Everybody's okay with me just rewriting the fraction like that? Now, why would I want to do that? It's because I'm about ready to rewrite tangent as a fraction, and I don't really want a fraction on top of another fraction. Like, that's weird to me. So I'm going to separate these two so that when I do that, I just have like one fraction times another fraction. It's really clear what to do. Is that okay? So if I look at, God bless this stupid flipping thing. Why is it that every time I touch you, you like cut out? Okay. If I look at my quotient identities, I see that tangent is equal to sine over cosine. So I can say tangent squared is equal to sine squared over cosine squared. Is everybody okay with that one? Now, why was it helpful to do that? It seems like, Mr. Kulik, this looks like it's getting more complicated. What advantage did I get by doing this? Great, yeah. Yeah, since there's multiplication in between these two fractions, I can cancel the sine squared in the numerator with the sine squared in the denominator. When I do that, what am I going to be left with? What's in the numerator? A 1. What's in the denominator? Cosine squared x. Very good. Does everybody see that? And can I do any better than that? It's not just cosine squared. It's, look at the reciprocal identities. What is it? Say it loud. You got it. Somebody's back there with like the right, basically saying it. Secant squared. Yes. Very good. SEC. Yeah. And we see that that's a little bit better than the previous because that's not a fraction, right? Still has one trig function in it, but we prefer a non-fraction to a fraction. Non-fraction is simpler. I think we'd all agree on that, right? Everybody's okay? How's this coming? This is going to be hard at first. Like if you're like, this is hard, I'm confused, that's okay, right? This is a new skill, and it's a skill that really like, you need some intuition about what to do because there's not really a set like solving an equation thing where we're just going to follow the reverse order of operations and every problem is kind of the same. I can give you some like general pointers, but sometimes the easiest way is going to be something you haven't seen before. And you're just going to have to kind of like see it and do it and go, oh, cool. Like, that's a neat trick. Maybe I remember that and can use it later. Or sometimes it's just going to be like, oh, that was just tricky. But in the beginning, you just got to kind of have to do a lot of these and play around with them and struggle with them and like get some feedback and get checked and like talk to somebody else and go back and forth about what you can do or what you can't do. But in general, like, in my experience, the biggest stumbling block for students beginning on these is their algebra skills. Is they start doing things that is not okay to do algebraically, and that's why they get things wrong. It's not the trig identity part. It's that like you canceled fractions across an addition symbol, or you didn't make a common denominator, you just added numerators and added denominators or something, you know, or you do something that you can't, you know, like you cancel something in a fraction where you cancel a piece of an addition problem with the denominator. You know, like things like this that are not, the trigonometry is not the problem. It's the stuff from last year, the algebra, that's a problem. But we'll keep going. We're going to do some more of these, and then we'll stop and let you guys work in some small groups to work on some of these, so you can talk and collaborate and like ask some questions, and I'll walk around and help and look at what you're doing and give you some feedback so that we can kind of help start building out some intuition about what to do. Okay, Emilio? Mm-hmm. Sure. Okay, this is our last example that we'll look at here today. So we have cosine x over 1 minus sine x over cosine x. Any algebraic thing that you'd want to do here, Landon? Now, that's it. Here's an important clarification question. Can I cancel the two cosines across the subtraction symbol? No, right? If that was a multiplication symbol, all day long, cancel away, my man. Across a subtraction symbol, though, no dice. So what should we do here, then? I would say there is an algebraic thing we should do here before we start looking at identities. What's simpler than two fractions? One fraction, right? So what would we have to do to do the subtraction there to get one fraction? What do we have to have? A common denominator. Very good. What would the common denominator be in this case? Victoria?
1 minus sine.
1 minus sine x times cosine x. Would just be the product of the two denominators, right? Since those two denominators are relatively prime, there's nothing in common between 1 minus sine x and cosine x. Maria, you're stretching?
Yeah.
Okay, no problem. I just saw the hands up. I just want to double check. So I'm going to multiply the first fraction by cosine x over cosine x, and multiply the second fraction by 1 over sine x, or 1 minus sine x over 1 minus sine x. Everybody's okay? All right. So my denominator is that now. Everybody good? Cosine x times cosine x is cosine squared x. And then I have negative sine x times 1. That's negative sine x. And then negative sine x times negative sine x. That's positive sine squared x. Is everybody okay with what we did to make our common denominator there? We can see now that like the algebra part is sometimes maybe the hardest part, right? If our algebra skills aren't real solid and we're, not making common denominators properly or like adding fractions properly, you can see that like if you can't do that, everything after it's going to be an issue. You know what I mean? So we have to be very careful on that stuff. But we now have one fraction, right? That's great. Notice that I didn't multiply the denominator out. Why did I just leave the denominator in that form? So remember back to algebra 3-4. If I'm going to reduce a rational expression, it has to be in factored form. Everybody agree with that? So at some point, if I'm going to do some reducing, I'd have to factor that denominator. Why would I multiply it out to get it out of a factored form? I wouldn't. I'm just going to leave it in a factored form. Is that okay? The numerator, we have to do the subtraction in there before we can do any factoring, though. Okay. So at this point, we've made our common denominator. We did the subtraction. Is there any other algebraic thing you think we can do here? Can I cancel cosines? Or cancel one of the signs from the numerator and denominators? No. Why not? Remember when reducing a fraction, I can't reduce part of an addition and subtraction problem, right? Because I have stuff added to that cosine squared. I can't reduce part of the cosine squared with part of the denominator. has to be like the whole shot or nothing, right? You have to have it in a factored form. So there's no more algebraic things to do here. Do you guys see an identity that we could use here? I see one right away. Yeah, since I have a sine squared and a cosine squared that are being added together, even though they're not right next to each other, it's okay. They're both positive, right? They're both part of the same addition and subtraction problem. That's okay. We can use that Pythagorean identity there to turn that into really 1. We still have the minus sine x in the numerator. And the denominator we didn't do anything to. Everybody okay to hear? You guys see anything to do now? I see an algebraic thing that I would like to do. Can I cancel what? Yeah. So I can cancel out the 1 minus sine x's from the numerator and denominator. Is everybody okay with why I can do that now? Because it's the entire addition or subtraction problem. It's okay to do that reducing. Cool? Okay. What do I have left after I do that reducing? It's not cosine x, because where was cosine x before? In the numerator denominator. It's in the denominator, right? So it still needs to be in the denominator. What would have to be in the numerator then? 1. Again, easy algebra mistake to make. We have to be careful about those things. But this is why we're doing this, going slowly and trying to do this together, and why we'll take some time and let you guys work on some stuff on your own. Okay. What do you guys want to do from here? Can we get better than this? What does this become? Secant. Very good. Okay. We're going to stop here. What I'd like for you guys to do for the remainder of our time here is to find a partner and work on these last 4 simplifying expressions on the notes 02. So these 4 problems here. Oops. Why did it jump all the way there? I'll leave this up. But work on these. You could just do this on a separate sheet of paper. It's for nothing more than practice. If you have questions about things, I'll be kind of up and moving around. If you want to ask me about what to do or if what you did was okay or any of these sorts of things, I'll be happy to assist. But I would like you to find somebody and we'll work on this for the remaining 20 or so minutes of class that we have here. 10 minutes, whatever minutes, 15, something, I don't know. Some minutes of class. But please, please, please do something.